Hi, and welcome back to Statistics Online. Today's lesson is about sampling distributions of the mean. And you can see I'm in a different location today. This background seemingly looks fake, but I assure you this is the real deal. Real old books. So we know that today is important. Anyway, being a little facetious, but it is indeed one of the most important subjects in statistics, the sampling distribution. We begin with sampling error, which is a concept in general that describes the difference between a sample statistic, okay, and its corresponding population parameter. So we could be talking about the population mean, and when you draw a sample from that population and calculate x bar, your sample statistic, the difference between those values is called sampling error. All right, it's error that occurs because of a sample. Don't confuse it with some sort of calculation error or mistake. It's not a mistake, it's a difference between a sample statistic and its population parameter. Because we're going to be taking different samples, or different samples are possible from a population, we'll talk a little bit later about how many unique samples can be drawn from a population of a fixed size. We're going to have different sample means that could occur for each different sample. And because we have different sample means, therefore, the sampling error, the difference between the population and sample statistic, differs. The point, and here's an example here, this is x bar, the sample statistic, a subscript I to denote this is a distribution of x bars. Various x bars can be drawn from that population. Mu is a parameter value, so it has no subscript. And the point is that the sample mean is a random variable. All right, sample mean is a random variable, and thus it's going to have its own distribution. I made mention of this in the previous slide, but how many different samples can be drawn from a single fixed population size. The question of how many unique samples you can take is an exercise here in arithmetic. How many different sample sizes how many different samples of size 4 could be drawn from a population of 60? And you notice we have small n for the sample size, capital N for the population size. And the combination formula as follows, where you have the factorial sign. So the numerator, for example, is 60 times 59 times 58, and so on. And the rest is pretty simple. You're drawing 4 from a population repeatedly, and so from a population size of 60 and repeated samples of 4, you could get 487,635 unique samples of size 4. That's kind of important. A relatively small population size of 60 and a small sample size of 4, you can generate almost 500,000 unique samples. And this is going to be important because it would be these 487,635 samples that would make up the distribution of x bar. So sampling distributions, very simply, it's a distribution for a sample statistic. So if I can take many samples from a population, and every time I can calculate a statistic, and if I organized all those statistics, then I would have a distribution. All right, and like as we were talking about with population data in previous lessons, now this distribution of sample statistics will have its own shape, its own measure of central tendency, its own mean, and its own measure of variability, which we like the variance and the standard deviation. So the question is, or we would like to know, what is the mean? What is the standard deviation or variance? Right, those give us the same amount of information. And what's the shape? And the shape is important because we've concentrated a lot on the normal distribution and our ability to use the standard normal table when we can approximate a distribution as normal. And, well, it would be nice to continue that. Okay, so a true sampling distribution. What I'd like to say here is that most of the time when we're talking about sampling distributions, we're talking about it in a theoretical way. And the reason is because it's very hard. It's very hard, or in many cases it's not possible, for us to construct a true sampling distribution, because a true sampling distribution requires all possible values for a sample statistic. All right, that means that if you have a population size of capital N and you're taking a sample size of little n, to get a true sampling distribution, you need to take all possible samples, all of those 487,635. All right. So two things. Here on the side, if we need all possible samples of a given size, that means you need the population distribution. Which, first of all, should look odd because as we move forward with statistics and we get into inferential statistics, the whole point of inferential statistics is that we don't have a population. We have questions about a population data set that we can't directly answer. And so we sample from that population to try to infer those characteristics. Well, there's no need for inferential statistics if you have the population of interest, and there's no need for us to be talking about sampling distributions if you have that population. And so this can be confusing, but hopefully it's not. The point is that these sampling distributions are going to have certain properties that carry over. So even if we can't observe a true sampling distribution, we're going to know about some of these characteristics that will be there. Okay, that these populations will hold. All right. So here we are. Can we say something in general about these properties? The answer is yes. And I'm going to look at a simple example to at least highlight the first property, which is the mean of this distribution, the measure of central tendency. And so to do so, let's look at the small population of students. And these 4 students skipped the following number of classes last semester. All right, slackers, these guys. We've got Zach, who clocks in at 4 classes skipped. Then Slater. Student's name is Slater. Imagine. Anyway, Slater misses 8 classes last semester. Horrible. Kelly, right? Kelly misses 6 classes. And Screech, the student Screech, misses 4. Let's consider this 4-person make up our population. Of course, this is a silly population size. Not a silly example. Silly population size, but manageable. And we can do the arithmetic in our heads. So what's the population mean? Well, if I add up all of these observations, these 4, and I divide by 4, then I'm going to get 5.5 skipped classes. Okay? So 5.5. Now, let's form a sampling distribution of the mean from this small population size. And to do so, let's take all possible samples of size 2 from this population. All right? And if I took all... Let's go here for a second. If I was to take all possible samples, those would consist of the following. I would have Zach and Slater. I would have Zach and Kelly. I would have Zach and Screech. I would have Slater and Kelly. I would have Slater and Screech. And I would have Kelly and Screech. And the pairwise number of skipped classes would be the following. Okay, and the x bar, the mean, would be, of course, adding those 2 pairs and dividing by 2. Right? We're going to have 6, 5, 4, 7, 6, and 5. And if you add up this column here, well, first off, this column is a sampling distribution for the mean. That's all possible samples of size 2, and from all possible samples we calculated x bar. So that is a sampling distribution of the mean. We'll go back to this in a second. Let's copy it. So the first property of a sampling distribution is the following, that the mean of a sampling distribution equals the population mean. All right, in notation form, the mean of sample means, mu sub x bar, equals mu. So mean of sample means equals the population mean. Now, when the average of all possible values of a sample statistic equals a parameter, we have a special term for that. That's called an unbiased estimator. Okay, that means that x bar could vary. All right, it could be less than the population mean, it could be greater than the population mean, but an average is going to equal the population mean. All right. Now, to verify this property, all we have to do is take our column that makes up our sampling distribution and find the mean of sample means. Right. So, what are the mean of means? And here, again, is our sampling distribution. This column adds up to 33, and 33 divided by 6 is, again, 5.5. So it's 5.5 skipped classes, which equals the population mean. So we verified that first property. The second property of a sampling distribution around the mean is that the standard deviation, okay, which has its own terms. So the standard deviation of a sampling distribution is called the standard error. And we're going to be using that term throughout this course, the standard error. So it's something to definitely commit to memory. The notation is slightly different. We're using this lowercase sigma, like the population standard deviation, but where here this is the subscript x to indicate the variable x. The subscript here is x bar. All right, the subscript here is x bar. So this is the standard deviation of sample means. This is the standard deviation of the population data. And so the standard deviation of sample means, the standard error, is going to equal this ratio, the numerator being the standard deviation of the population divided by the square root of n. Okay? So as your sample size gets up, this denominator goes up, this denominator gets bigger. Okay? And as the denominator gets bigger, hopefully you can see that the relationship there is that the standard error goes down. If we look at this data, and this data is extremely interesting, it's on the weight of pumpkins from pumpkin patches in Massachusetts. So, pretty thrilling stuff. These are partial sampling distributions, again, not full sampling distributions. These are 200 sample means. Each you can look at the red graph and the green graph separately. Let's start with the red one. The red one is a depiction of 200 sample means of size 4. So for each of these sample means, someone gathered 4 pumpkins, put them on a scale, added up all those weights in pounds, whatever, divided by 4, and that's x bar. And we have 200 x bars. Okay, 200 x bars from samples of size 4. In the green graph, it's the same thing, 200 samples, 200 x bars, but those x bars are taken from samples of size 9. So each time we have an x bar, it's 9 pumpkins on the scale, divided by 9. All right? And what you can see, or hopefully what you see, is that these two distributions are centered around the same area, right? The measure of central tendency is gathered around 40 pounds, which is probably close to the population mean. But the variability in the red graph is more than the variability in the green graph. The green graph is tighter and taller around its mean. And the reason is that the standard error, the standard deviation of the sampling distribution in green is less than that of red because we're dividing by the square root of n. All right? So numerically, we're dividing by the square root of n. Intuitively, we're just gathering more pumpkins from the population each time we take a sample, and so we're going to be tighter around that true population, that mean. And so as I increase n, I should expect these graphs to become tighter and taller around the mean. Here we have an example. The population mean for the normally distributed miles per gallon of all Toyota vehicles is 40, and the population standard deviation is 10. All right, that's population data. Now, the question here is, what is the standard deviation of the sampling distribution of sample means when n equals 100? All right, so the sample is 100. Well, the standard deviation of the sampling distribution, again, is called the standard error. And the standard error is going to be the population standard deviation divided by the square root of n. And so we just plop it into the formula. Notice that this is just, it's the same formula rewritten. Here, this is the notation. This is expanded notation. And now I'm just plugging in 10 and the denominator is square root of 100. So we're looking at 1 mile per gallon is the answer. 1 over 1, 10 over 10. So what I want to demonstrate is the difference between these, so far, the difference between the population data set and its the distribution of sample means drawn from that population. And so we look at this problem here. The population mean for the normally distributed miles per gallon is 40. Okay, so mu is 40, and sigma, the population distribution, is 10. And we were taking samples of size 100, and this question had asked what the standard deviation is for the sampling distribution, what the standard error is. Now what I'm going to do is write down these characteristics. All right, and highlight where these differences would lie. So the population data set, okay, which is X, this is miles per gallon. Notice X, it's on the axis. Centered at 40, and a standard deviation, we'll put in, I guess we'll put in all three here. 10, so 50, 60, 70, I'm going. 3 standard deviations in all directions. This is the population data set. All right, so this is population. Now, if I'm taking repeated samples of size 100 from this population, and every time I take a sample of size 100, I calculate X bar, same units, miles per gallon, well, the first property of the sampling distribution is that the mean of all these means is going to equal the population mean. So it's also going to be 40. I haven't talked about the shape yet. I don't know what the shape of this is. Okay, so I'm going to leave the shape absent right now. But the standard deviation of this distribution is not sigma, okay? It's sigma divided by the square root of n. So the standard deviation of this distribution, aka the standard error, is 1. So 3 standard deviations away from the mean, looks like this. Okay? Now, lo and behold, in the next lesson, we'll talk about the conditions necessary for this distribution to actually be normal. Right now, we haven't gotten there, so I'll take that away. But notice that the standard deviation of this population is 10. The standard deviation of the distribution of sample means is 1. All right? And this relationship that the standard deviation of the sampling distribution will be strictly less than that of the population is important and one that we'll maintain throughout. And so this final slide, will the standard deviation of the sampling distribution equal the population standard deviation? The answer is no. Okay, it gets smaller as n gets larger, and we know that just strictly from the formula. As I increase n, the denominator goes up, and therefore the standard error goes down.